one video. Welcome to the video to experimentally understand why the nice sets will form a sigma algebra. And in this particular video, in this first video, we'll try to take some time to spend up the tools we require to proving the main theorem. Main theorem is like proving all the nice sets forms a sigma algebra. It's like sigma algebra means the empty set and whole set belongs to it, and it is closed under complements and closed under countable unions. And what is measurable set, we'll try to discuss. Sorry, measurable or nice set, we'll try to define it properly, and we'll get into the detailings. So here we'll prove some short results, some 3 to 4 short results which are required for the next video. Let's get started. Yeah. So the first one, the definition of measurable set. A set is a subset of R. I'm just talking about subsets of R. You can replace with any X for that matter. Subset of R is measurable set if there exist subset of R is measurable if there a set is measurable if m star of A intersection E plus m star of A intersection E complement is equal to m star of A for any A subset of R. And recall that m star of A means, for the time being, which is nothing but infimum of all the sets, infimum of summation of length of ions, where n belongs to natural numbers, such that A is contained in union of ions, where ions were open intervals. This is a definition, open intervals. So this is our main point. And observe here, the simple observation tells us A is equal to, I can write it down, A is equal to A intersection E union with A intersection E complement. So the m star of A is always less than or equal to m star of A intersection with m star of E complement. So this is by subadditivity. So then it is enough to prove that m star of A is greater than m star of A intersection E plus m star of A intersection E complement. So this is the thing. I'll just write it down like this. For suppose it is just for my sake of clarity, I'll write my inequalities on the right side. What I mean is m star of A intersection E, m star of A intersection E complement is less than or equal to m star of A. So this is a this is a definition. Just look it for 10 seconds. This is what our set is said to be measurable if m star of A intersection E plus m star of A intersection E complement is equal to m star of A. For that matter, this one-way inequality is enough. It is enough to prove this one. If it is measurable means, so we'll write it down formally. So a set E is subset of R is measurable. If m star of A intersection E plus m star of A intersection E complement is less than or equal to m star of A for any A subset of R. Okay. So this is our definition. Now we'll get into the first problem, or first toy problem, I would say. First toy problem. So let E comma F belongs to M. For me, M means measurable sets. then E union F is equal, E union F is also belongs to you. So before doing any problem in mathematics, try to understand what they given. So E belongs to M means if and only if M star of A intersection E plus M star of A intersection E complement, which is less than or equal to M star of A. Okay, this is what we have been observing. This is what I am looking into things. So F belongs to M means M star of A intersection E plus M star of A intersection E complement is less than M star of A. So, and at the same time, I'm ignoring the cases when M star of A is equal to infinity. So if M star of A is less than equal, sorry, is equal to infinity, everything works nice. But I'm assuming, but we are assuming M star of A is less than infinity. So less than positive infinity. Now, so with the given data, our goal is to show that M star of A intersection E union F plus M star of A intersection E union F complement, which is less than or equal to M star of A. This is our main goal. So this I will keep it in mind. So my idea is to not to give a line by line proof. That's not my main of this entire channel. It's the main idea is to explore with the things, explore into the things. It's like, okay, let's get into the things. For suppose M star of A intersection E union F. So we'll just keep it like this. Or for that matter, okay, if we explore it, what we'll get it? So which is nothing but M star of A intersection E plus M star of A intersection E F complement. We can write it down. I'm exploring, I'm saying it again. So we can write it down exactly if we can able to use the De Morgan's clause. This is F complement. So the question comes into the picture is, for suppose if we have, my idea was like, okay, we did not have any interlinkations. For suppose if we have M star of A intersection E intersection with F, sorry, E complement intersection with F, what does it mean? For suppose if we have these two, what we can do? For suppose if we have this term and if we can able to add these two, which is nothing but M star of A intersection E. So what I mean, I'll put it in a proper way. If I have these two terms contribute to E in E complement intersection with F complement plus M star of A intersection E complement with F, with both will contribute to M star of A intersection with E complement. So the question arises is, okay, you have this term, it's nice, you have this term, can we just think of this as a substitute for A complement? This is a substitute for this term. Can I just think of these two can be substituted, or in the sense these two can be interchanged? I'm talking very loose here, but let's put it in right words. For suppose A intersection with E union F, so which is equal to A intersection E union with A intersection with E complement intersection with F complement. So this is very easy. For suppose any X belongs to A intersection with E union F, this implies X, okay, which is nothing but A intersection, you just think of A intersection E union with A intersection with F. I'm using distributive law of sets. It's like X belongs to A intersection E, or X belongs to this. Okay, fine, this is nice. So we can say that A intersection with E union F, which is a subset of A intersection E union with A intersection with E complement. Other way inequality, sorry, other way inclusion also you can prove. It's an easy exercise or easy observations. Observe here. Okay, if you are, just take a pause and just do this exercise. Is it okay? And whatever I am writing down, for 10 seconds, 10 to 20 seconds. Just do it with a pen and paper. Pause for here, pause the video here, just do it for 10 to 20 seconds. You need to convince yourself. It's very basic set theory. So now it comes into the picture. Okay, I have this idea. Rather than putting like this, A intersection union F, rather than using this whatever the known result I have, so can I use this as, which is equivalent to saying that can I use these two terms? For suppose, so if I can able to write down this, so which will be less than or equal to m star of A intersection with m star of A intersection with E complement is less than F. And so we have m star of A intersection with E union F plus m star of A intersection with E union F whole complement, which would be less than or equal to m star of A intersection with E plus m star of A intersection E complement intersection with F plus m star of E intersection with F complement. So which would be, so see these terms here, so which is nothing but m star of A intersection with E complement. So since E is measurable, so I can write it down m star of A. So here I use the fact for these two terms. So this is acting as my E, this is acting as my A, this is acting as my A. So these two terms will combine to give it to me by, since F is measurable, here I am using F is measurable. So here I am using E is measurable. So finally we got our conclusion. So finally we can say that A intersection with A E union F belongs to M is nice set. We can say that the union is also nice set. So observe the simple things here. I mean, don't jump into the just take a pause and relook yourself and convince yourself that how we got it. I mean, this observation, first one, this is our first main observation, how we got this one, first one. And second one is how we got that observation, and second one is how we proceeded the proof. It's like we used F is measurable here and E is measurable. Okay, and pause this video. If you can able to, just close down your notes and take some rough paper, again a very rough paper, and write down the proof again. Just take some couple of minutes and write down the proof wherever. For suppose if you can able to reach to some certain extent, it's fine. If you stuck it there, just go back to this proof and do it again. It takes 5 minutes, extra 5 minutes, it's fine. But by the end of 20 minutes, roughly around 20 minutes, you'll be understanding this proof. This video might be 30 minutes, you're doing extra 7 to 10 minutes to understand the things, rather than postponing or procrastinating to I'll do it later. Just do it now. Be comfortable, and once you're understanding, you'll enjoy it. If you don't understand, you'll irritate and stress. So our main goal is to understand. Okay, let's do some color reading. Very simple color reading. So the corollary says that E belongs to M and F belongs to M. Then E intersection F complement belongs to M. So how it will be possible? So observe here. See, M star of E belongs to M. Does it imply E complement belongs to M? So what does it mean by E complement belongs to M? E complement belongs to M if M star of A intersection E plus M star of E complement. Okay, let me write it down properly. E complement, again it went right wrong. E complement of complement, which is less than or equal to M star of A. So which is same as, for suppose E belongs to M, which is nothing but M star of E intersection with E complement M star of A intersection E complement, which is less than or equal to M star of A. So both the things were same. E belongs to M if and only if E complement belongs to M. And if you can able to observe that, if you take E is equal to R, still it works. E is equal to R and E is equal to empty, simple exercises which are belongs to M. Just pause here. Again pause, do this, pause, do, pause and do, understand and happy. Make yourself happy, convince, understand the things and enjoy the things. Okay, now, okay, we have understand that, okay, we have made a simple observation. This is a simple toy exercise, simple toy observation. I'm just giving it as a some exercise. Okay, this is a toy observation. So, and one more aspect. For suppose De Morgan's law. What does De Morgan's law says? For suppose I am saying E intersection F is also belongs to him. So how it will be possible? For suppose E intersection F, can I write it down like this? E complement union with F complement intersection with complement. So this belongs to M. This belongs to M. Union will belongs to M. And since union belongs to M, then complement will also belongs to M. So it's somewhere sense that, okay, E belongs to M and F belongs to M. This implies E complement belongs to M if and only if E complement belongs to M, comma F complement belongs to M. Then E union F belongs to M. E complement union with F complement belongs to M, and E complement union with F complement whole complement belongs to him. That is same as E complement intersection with F belongs to him. See here, I did not prove the main result. I just bombarded. I mean, I was just been done. So here, okay, it's a moment of pause. I'm just giving you a pause. E belongs to him, and F belongs to him. Convince yourself. E complement, E intersection with F complement belongs to him. Okay, I'm again pause. Do, understand, happy. It's somewhere on very similar lines like Professor Kumarison's videos like pause, review, proceed. But I'm the very big fan of his lectures. Yeah, I was just following his footsteps. I can say that. Okay, pause, do, understand, happy. Very simple to like that. Okay. Okay, very equivalent. You can just say that it's an equivalent. Yeah. So we have proved some two results. Yeah. Now we'll go to the third one. And one more. It's very basic set theory. We'll do some two set theory things. And we'll go to the things. So where we are. So the second result. Second result would be, okay, let E belongs to M. E and F are nice sets. I'm saying nice sets or measurable sets more formally. Nice sets. And E intersection with F is empty. And our goal is to say that, over then A intersection with E union F, which is equal to M star of A intersection with E plus M star of A intersection with F. So let's write down. So what would be like this? For suppose you just think of, can we write it down like this? M star of E directly, can we attack this M star of A intersection with E union F, which is equal to M star of A intersection with the E union F intersection with E plus M star of A intersection with E union F intersection with E complement. I am using E belongs to M. This is my A. This is acting as my A. This is acting as my A. This is acting as my A. Acting as my A. Since, okay, with further do. For suppose E belongs to M, I'm recapping again. if and only if m star of a, which is equal to m star of a intersection e plus m star of a intersection e complement. So now comes into the picture. Now, okay, this is very simple. For suppose, okay, just it's a movement of hands. So which is nothing but, if you can able to observe, just a set theoretical observation, a intersection with e union f intersection with e, which is equal to a intersection e, and a intersection with e union f intersection with e complement. Can I write it down this as a intersection with f? I'm saying it again. Pause, do, understand, and be happy. So that's where the result, our result is done. If you can able to plug in these two things, or should I use this now? This implies, so m star of a intersection with e union of, which is equal to m star of a intersection e plus m star of a intersection with f. So the simple observation is, observe here, observation is pretty simple. And okay, I'll give you one thing here. I'll give you one simple exercise here. Observe, can you drop something? Can you drop one condition? Can you drop one condition? One condition in assumption. Can you drop one condition in assumption, and still this theorem will hold? Still this theorem hold? Think. Pause for pause a minute. Pause a minute. Think. If you don't get the answer, it's okay. It's okay. It's okay. Give your try. Okay. Okay. I hope you have paused this video and done this. If you can able to observe that we have used only this E belongs to F. So we can drop down that. We can drop down a condition that E belongs to M and E intersection with F is empty. But we have used this fact. Okay, we have used this fact to write down this. So the simple observation is, okay, from here we can just say that E belongs to M and F be any subset of R with the E intersection with F is empty. We can say M star of A intersection with E union with F, which is equal to M star of A intersection with E plus M star of A intersection with F. Yeah, isn't it so good? So for any set we can just think of, we have proved some much more stronger result. For suppose, can you write it down something else on here? So observe here, one more observation I can write it down. See here, A is equal to R. If I take A is equal to R, then A is equal to R, then M star of A union with F, which is equal to M star of E plus M star of F. So in some sense, for suppose E and F, okay, observations were, observe that E comma F belongs to M and E intersection with F is empty, then they are closed under additivity. The additivity is going to happen very smoothly. E intersection with union f, which is equal to m star of e plus m star of f. So somewhere around, I mean, the motivation is simple. For suppose nice, why all the sets? For suppose outer measure is an idea of outer measure is an idea, is an extension of length, is an extension of length to all subsets, to all subsets of R. But we fail, but we fail but we fail to do for all, do for all. Yes, I mean, do for all R, entire R. But I mean, one video will discuss on all this also with this counter example also. For the time being, we can't do the length, length extension to all subsets of R. So we need some special sets. We call that special sets as a, so we need some special sets. So we need some, all entire R means all power set of R. Here I'm very clear, power set of R. We need some special subsets. We need special subsets which are, for suppose A which is sitting, or M, nice sets which are sitting properly under power set of R. So this will form a sigma algebra, and we'll talk about all these things where this will have, this has the additivity. What do you mean by additivity? Additivity is nothing but m star of A union B is equal to m star of A plus m star of B when A intersection B is empty. So this is what our observation is. For suppose our main goal is to find an extension of length. Somewhere around we have defined outer measure, but it fails at that additivity property. It's like this additivity property. Then we are just thinking of, can we have some collection of subsets of R where the additivity makes sense. So we are just saying that where this additivity makes sense on that particular collection of, particular sets or special sets where the additivity makes sense, we are calling the special sets as nice sets or measurable sets. Okay, this is a bigger picture. Keep the bigger picture in mind. Okay, this is a bigger picture. Now, okay, now we'll end up with some simple some simple set results, set theory result. Simple set theory. So it's very simple. For suppose A comma B are any two sets, for that matter, I'm just calling C is equal to A and D is equal to A minus B. I can say that A union B is equal to C union D, and we will construct, okay, this is just check it. So we will construct any n sets E1, E2 and so on En. F1 is equal to E1 and F2 is equal to E2 minus E1 and so on. Fn is equal to En minus union of I is equal to 1 to n minus 1 Ei. So our claim is to say that, our claim is to write down, our claim is union of Fn's where n is equal to 1 to k, or k is equal to 1 to n, sorry for that matter, which is equal to union of k is equal to 1 to n ek. So this is our goal. Sorry, this is an exercise. This is an exercise, simple exercise, simple take home exercise. Take home exercise, and here we finished all the ingredients to prove this countable union is measurable. This is the content for next video. content for part 2. Okay, until then, see you, bye and goodbye. Sorry, see you and stay safe.